In contrast to spectroscopy, photometry is a technique of measuring the flux or intensity of an astronomical object's electromagnetic radiation. Instead of looking through the telescope with eyes, a digital camera is placed so the CCD array is at the focal point. The digital images are analyzed to identify and characterize astronomical entities. Usually a filter wheel is put in the optical path so that images are recorded for a broad but specific region of the electromagnetic spectra. A spectroscope splits the light into different components. In spectroscopy, the spectrum of an image is recorded on a CCD array. The resulting spectrum is analyzed to identify chemical composition, radiation from the object is greatest is related to its temperature. In this particular equation, one wavelength is measured in nanometers and temperature is measured in Kelvin. 1 nanometer is 10 to the minus 6 meters, or 1/1,000,000th of a meter. Wien's law enables us to estimate the temperature from the peak wavelength of a celestial entity. In the upper right, you see a very cold cloud, which is obscuring the clouds behind it. Next down, you see a hotter nebula region. And then we have the sun, which peaks in the visible spectrum. And below that, there's a globular cluster of many stars, which are all very hot. The second radiation law is the Stefan-Boltzmann law. The Stefan-Boltzmann law says that the total amount of energy per unit surface area per unit time radiated by a source is proportional to the fourth power of its temperature. Unlike the measured brightness area, which depends on distance from the source, the unit area here is on the radiating object. Here the flux is the amount of energy per time emitted by the surface area on the star as measured at the star. The luminosity of the star is the product of this flux and the entire surface area of the object. When the radius and temperature are known, we can determine luminosity of the star. The luminosity is the product of the emitted flux at its surface and its total surface area. The nature of gravity gives us informed intuition that stars will be circular or ellipsoidal if they are rotating at a high rate. We haven't found a cubical star, so recall the surface area of the sphere is 4 times pi times the radius squared, and from this and the Stefan-Boltzmann law, we can write a relationship for luminosity in terms of temperature and radius. These laws explain why Betelgeuse at temperature of 3500 Kelvin is red and why Rigel at 12,130 Kelvin is blue. We also related the flux to the size of the stars. When Betelgeuse explodes as a supernova, it will be brighter than our full moon for several months, and this could happen at any time for the next million years. Consider now Rigel and its temperature of 12,130 Kelvin. From 1 astronomical unit, that's the distance from the Earth to the Sun, it would have an angular diameter of 35 degrees, and it would be 85,000 times as bright as the Sun. In fact, the flux at Earth would be like that of a welder's arc measured at a few millimeters distance. Rigel is about 8 million years old. It is intrinsically the brightest star in our neighborhood of the galaxy. It is 24 solar masses. Wien's law and the Stefan-Boltzmann law, however, don't explain why the Orion Nebula gas cloud appears pink, and that'll be explained in these topics about spectroscopy. Recall figure 4.7. By convention, the electromagnetic spectrum is broken into loosely defined regions ranging from gamma rays to radio waves. For most of our astronomical images, the caption includes a labeled icon to identify what part of the spectrum was used to make the image. Gamma rays are G, X-rays are X, ultraviolet is U, visible light is V, infrared is I, and radio is R. If more than one region of the spectrum was used, multiple labels are highlighted in the icon. Different celestial bodies radiate energy in different spectral regions. The hazards, as a rule of thumb, are that high-frequency radiation can rip apart atoms in your body, whereas the low-frequency radiation can cook the cells in your body. Gamma rays are the most energetic and cause harm to life since they damage cells and make mutations occur and even cell death. The atmosphere absorbs cosmic rays and X-rays, so these have to be measured from telescopes on satellites. Since they have the highest frequencies, they have the shortest wavelengths. They're on the order of the size of the nucleus. They are produced by neutron stars, black hole accretion disks, and superhot solar corona and supernova remnants. The highest ultraviolet frequencies also cause severe damage to cells. Lower frequency ultraviolet is less damaging but does cause sunburn. Ultraviolet light is produced by hot, young O and B stars and supernova remnants. Visible light is generally safe, but bright sources such as the sun can damage our eyes, even leading to permanent blindness. Stars and warm gas clouds radiate visible light, and dust regions in the solar system bodies reflect visible light. Infrared radiation is felt as heat and causes skin burns. Microwaves can cause internal heating of body tissues. Infrared light is emitted by cool clouds of gas, dust, planets, satellites, asteroids, and all living things. Radio waves are emitted by cold gas and star-forming regions. There are two main ways that optical devices split light into a spectrum: differential refraction and interference. In differential refraction, a prism disperses the light because the speed of light in the prism is wavelength dependent. This causes the different colors to refract different angles. Reflection and transmission gratings cause light to interfere with itself, selecting narrow bands as throughput, creating a spectrum. The back of a CD behaves like a reflection grating, and that's why they are shiny and have a rainbow spectra. Gratings have many parallel grooves. The width of the distance between peak and the first zeros on either side is the wavelength divided by the product of the observer distance and the cosine of the reflection or transmission angle. Blazing is the tilt of the groove surfaces that has an angle designed to concentrate light towards a certain direction. In Chapter 4, the concept of spatial resolution was introduced. For an aperture diameter d and wavelength of lambda, spatial resolution in arc seconds is 2.06 times 10 to the 5 lambda over d. Thus, the larger the telescope diameter, the more detail that can be seen on a distant object, as the UNL telescope simulator illustrates. Similarly, diffraction gratings have spectral resolution, that is, the minimum wavelength interval that can be measured. There are three different types of spectrum: continuous, emission, and absorption spectra. When passed through a prism, white light produces a spectrum containing all colors. Black bodies also have continuous spectra. An atom or a molecule in a heated gas radiates at specific wavelengths. These are emission lines. A spectra of emission lines is called an emission spectra. If light of all colors from a source of a continuous spectra are passed through a cool cloud of atoms or molecules, the cloud is heated by radiation. The atoms and molecules excite by absorbing light of a particular wavelength. When the light is absorbed, there is a dark absorption line in the spectrum. Emission lines can also appear superimposed on fainter continuous spectra. Emission lines identify chemicals in a cloud. We'll study the Bohr model of hydrogen, which has a single electron, to see how electrons absorbs photons, putting it into an excited state, and once excited emits photons to return to a lower ground state. The Bohr model predicts the emission spectrum of hot hydrogen gas, and hence the absorption spectrum of cold hydrogen gas. Multi-electrons are more complicated because there are many more energy level transitions that are allowed. When an atom ionized, meaning it loses or gains electrons and no longer has a neutral charge, the energy levels shift, but the same transitions are allowed. These are the electronic states of the atom. Molecular spectrum are complex compared to atomic spectrum. We can envision a molecule as a system of springs and masses, with the incoming photon of light that resonantly drives the springs that have its frequency. There are several modes, vibrational and rotational, and these are like the electronic transitions in that they are also quantized. As a single atom, there are also electronic transitions of excited states. With these additional vibrational and rotational modes and many more electronic transitions, the spectra of molecules is quite complex compared to single atoms. When a continuous spectrum passes through a cool gas, atoms of the gas will absorb the same frequencies they emit. The sun emits a continuous spectrum, but the sun is surrounded by cooler gases that make up its atmosphere. Astronomers study the solar spectrum to see what chemicals exist in its outer atmosphere. In 1817, it was determined that the sun had hydrogen, sodium, iron, calcium, and other metals in the atmosphere. The entire spectrum has many, many lines. Helium was discovered in the solar spectrum in 1868 in a previously unidentified yellow spectral line signature in sunlight during a solar eclipse by the French astronomer Jules Janssen. Helium is named after the Greek god of the sun, Helios. Accounting for temperature effects, astronomers use spectral lines to measure the chemical composition of stars. Despite their different spectra, most stars have very similar compositions. Most nearby stars have a composition nearly identical to the sun's. Some of the more common elements are listed below with their abundances in the sun. The ratio of hydrogen to helium is generally very close to 3:1, as it is in the sun. In stellar astronomy, atoms that are neither hydrogen nor helium are called metals. Their mixture is about the same in all stars, but their contribution varies from less than 0.01% to as much as 3%. Recall that the solar spectrum is absorbed and scattered by the Earth's atmosphere before it reaches the Earth's surface. Radiation at sea level has windows where light has transmitted in the visible and near infrared region, but it also has opaque bands due to ozone in the ultraviolet region and due to water and carbon dioxide in the near infrared region. Absorption spectra can be represented two different ways. The absorption lines may be dark bands or a continuous spectrum, or a line plot of brightness versus wavelength may be created. See how the absorption lines are represented in the above graphic. Figure 10.10 in the book illustrates the lines of the hydrogen atom. Modeling the lines is the goal of the next lecture. Figure 10.10 in the book also illustrates how different atoms have different spectra. Composition of the gas can be determined by matching the lines. Recall the Doppler effect from the modules about light. The Doppler effect shifts an object's spectrum either toward the red or toward the blue. The direction and the magnitude of that shift depend upon the relative speed between the source and the observer. Figure 10.16 shows how the Doppler effect can be used to find the radial velocities of stars. The radial velocity curve of binary stars can be used to determine the masses of stars. One technique for finding exoplanets uses analysis of the radial velocity of a star to infer that it has a planet in orbit around it.